Thermodynamic model tuning HydraFLASH can be done in three ways. You either tune the model for VAX modeling tuning, or you can tune the model, the CPA model, the default main thermodynamic model of HydraFLASH, or the asphaltene model tuning. I will explain each by first explaining why I put this characterization and definition before the tuning. If you have watched these videos about fluid management, in that video I explained that for VAX and asphaltene calculations, the model needs to know which components, which compounds in the fluid are asphaltene or normal alkanes. So in order to perform VAX or asphaltene characterization, you need to first characterize the fluid and then perform tuning. So let's start about the CPA model tuning. There are many ways to define a fluid in HydraFLASH. You can either create a fluid from scratch, you can edit a fluid, change it, save it as a new fluid, you can characterize it with single flash data and PVT information. And when you have this fluid, either the PVT characterized fluid or a defined fluid, you can tune the model using experimental data. You can tune the model using saturation properties, using PVT lab test properties like separator data, CME, DLE, viscosity, or other experimental data which you have in PVT lab testing, or a combination of them. So when you have a fluid defined and ready, you can tune it with CPA model tuning. For VAX tuning, the story is a little bit different, because for VAX calculations, the CPA model is incorporated with Coutinho model. So we combine two models together to calculate the VAX properties, the VAX formation temperature, and the VAX content of fluid at specified temperature or pressure. To tune the Coutinho model parameters, you need to tune the Coutinho model parameters with WDT data. WDT stands for VAX disappearance temperature. And because VAX disappearance temperature is the thermodynamic point for VAX formation, we need WDT for Coutinho model parameters tuning. Please be careful. The VAT and WDT are different. I will explain more what is the difference between WDT or VAT data or WAT data. But for the concern of this slide and this section of the tutorial, just remember that for tuning the VAX model, we need WDT data. Okay, but as I said, for VAX calculations, we incorporate CPA model and Coutinho model. So when the Coutinho parameters are tuned, the CPA model parameters must be tuned as well, because it needs to represent the saturation behavior of the fluid as well. Okay, so what user can do is to first characterize the fluid with VAX content data, and then feed this characterized fluid into CPA model tuning, tune it with saturation properties, PVT lab test data, and then feed this tuned fluid into VAX model tuning, and then enter the WDT data and then tune the model. So wax characterization is a two-step tuning. If you directly tune the wax model after you characterize it, it tunes it. The WDT, the predicted WDT will be exactly as the WDT that you have to tune the model with. But it doesn't represent the saturation properties of the system because the CPA model has not been tuned. So if you want to tune the wax model in general, you need to tune two things, two models, because the wax model is actually two models, CPA model and wax Coutinho model. So if you want to tune it, you need to tune both models. For CPA modeling, you need saturation properties or PVT lab testing properties. For the Coutinho model, you need WDT data. However, for asphaltene tuning, you can, because it use a different equation of state, PCSAF, and PCSAF stands for perturbed chain statistical association fluid theory. It used PCSAF for tuning, and the characterization of asphaltene requires Sara analysis. You can characterize the asphaltene model, the fluid with asphaltene characterization, and then feed the characterized fluid into asphaltene model tuning. In this asphaltene model tuning, you have options to tune the model with saturation, with asphaltene titration data, with AOP data, which has been measured using depressurization, or a mixture of them. So in general, you have three main tuning in HydraFLASH: the CPA model tuning, the asphaltene model tuning, and the wax model tuning. Maybe you need to remember when we say wax model tuning, remember Coutinho model tuning, because wax model is a combination of CPA equation of state and Coutinho model. So to perform a wax model, you need to tune both Coutinho and CPA. So wax model tuning is a two-step tuning. First, characterization, then CPA model tuning, then the tuning, the Coutinho model using WDT data. But for flash calculation, for saturation properties, for viscosity calculation, it is you can define the fluid. You can either create a fluid or characterize a fluid using PVT data and single flash data, and then tune the CPA model using PVT lab test or saturation data or viscosity data. For asphaltene, you need to characterize the fluid using Sara analysis. When the fluid is characterized, it can be input in asphaltene model tuning, and then that will tune the model using all the data you may have in asphaltene, combination of them, titration data, depressurization data, or saturation data. In the previous slide, I have presented an overview of tuning in HydraFLASH. And in these slides and the next two, I'm going to explain each tuning modules in HydraFLASH. The first one is the CPA model tuning, and the next one is asphaltene model tuning, and the last one is wax model tuning. The CPA model tuning, as mentioned before, CPA is the main thermodynamic engine of HydraFLASH. We have other engines like SRK, Payne-Robinson, and VPT equation of states, but the CPA is the best and the default model of HydraFLASH. And it's basically responsible to calculate the fluid phase properties in HydraFLASH, and then when the fluid phase properties, say gaseties, densities, are defined, then the phase equilibrium equations, the mass balance, the energy balance can be solved. And you will see the results as the flash calculation properties, hydrate dissociation points, etc. So by tuning, we mean that when we want to tune an equation of a state, it means that we want to adjust the equation of state parameters so that the model predicts the experimental data which has been used for tuning. So for example, if you are using saturation properties, for example, bubble point of an oil, to tune the model, the parameters of the CPA model are adjusted or changed so that the bubble point predicted by the model be as close as possible to the experimental data. So that is the definition of tuning in HydraFLASH. Okay, so when a fluid is defined, or is characterized, or is defined, it can be activated in this menu. This is the main menu of CPA model tuning. It has different sections. The first section is the composition info. You activate the fluid from this drop-down menu, and this is a suggestion name for the tuned fluid. Is the settings of the tuning, which I will explain in the next video, and then which experimental data user is going to tune the model with. And this section is for saving the experimental data on the database, because entering experimental data, for example, for separator test or the CME or DLE may take a long time. So it's better that user only enter it once, and then it can be saved on the database so that user shouldn't enter the data all over again if he or she wants to do the tuning again. And the next section is data grid we have here for entering the experimental data, or when we load an experimental data, it will be appear here. The results, the objective function and the error of the calculations will be shown here live, and the resulting parameters, so the corrections to these CPA parameters are also shown here. Then these three buttons, this first, the middle one is to start the tuning. This one is to cancel the tuning, and this one is when the tuning is done and you're happy with the objective function and the error. You can add this to database, and it makes a new fluid. So it is very important to remember that when you define a fluid, this fluid contains all the model parameters in itself. So when you tune it, the parameters are adjusted. So to not changing the parameters of the first fluid, we have to make another fluid with the exact same composition and the compounds, but this time with different EOS parameters. So you may have the original fluid and the original underline or dot tuned fluid. So these two fluids are exactly the same except for the model parameters. So the first original fluid you can predict any calculations with that, but the second one has been tuned with experimental data. Okay, the next important point you need to remember is that as I mentioned before, you can enter any experimental data, PVT Lab Testing data in here, and you can save it to database. When you save an experimental data to the database, you connect that experimental data to the loaded fluid. You see this arrow? So you cannot use different experimental data for a single experimental data for different fluids, because the reason is that or the gas compositions, when you enter an experimental data and you enter multi-stage gas compositions and if you load another fluid which has less components in the system, then then the experimental data for the gas composition will be irrelevant. So it has to be connected. Any experimental data, if you want to save it to the database, it has to be connected to a fluid. So when you press this button, it reads which fluid is active, and then it connects these data to this fluid. And whenever you want to load a fluid, if you load a not connected experimental data to a fluid, it gives you an error saying that this experimental data has been entered and has been saved for a different fluid. So this is very useful. It helps you to know which experimental data you use for which fluid. Okay. So if you want to test one single experimental data for different reservoir, for different fluids, you need to enter the experimental data for all those fluids. But if you want to connect several experimental data to one single fluid, again, you need to enter and save all those experiments. So one fluid can be connected to so many experimental data, but one experimental data can only be connected to one fluid. Okay, so this settings tab, as you can see, this tuning setting button and the simulation button, they have separate window. The tuning setting is actually the settings that you're telling HydraFLASH, okay, so which compounds you want to tune the model with, which properties you want to adjust, which EOS parameters you want to adjust. You want to adjust TC, PC, eccentric factor, and the viscosity parameters or the volume shift, and which SODU components you want its parameters to be tuned. You can check in this panel. Or whenever you enter an experimental data, which experimental variable is more important for you. So for example, when you enter a CME data and the compressivity factor is not that important for you. However, the liquid density, the dead oil liquid density is very important for you. So you can use these handles to tell Hydra, just assign a number between 0 to 100. So 100, that means very important, and 0 means least important. So by playing and assigning a value, you're telling HydraFLASH how much these parameters are important to you. These parameters are also called weighting factor, but I'm not trying to use mathematically known terminology, but again, if any parameters, for example, saturation pressure or density is very important for you, just assign a value with respect to the other values, and HydraFLASH, when it's tuning the model, it gives priority to those parameters with higher values, with higher assigned values or weighting factors. Okay, so I think the CPA model tuning presentation is now completed, and we can proceed to the next tuning. Okay, in this video, I'm going to show you how you actually can tune the model using the CPA model tuning, the VAX model tuning, and S14 model tuning. To tune a model, you need to navigate to the calculation tab up here. And let me close this one. And then for performing CPA model tuning, you just need to press this button, PVT Lab Test Tuning. And for VAX tuning, this is the button in the VAX modeling section, subsection. And for the asphaltene modeling, you need to press this button here for asphaltene model tuning. Okay, let's start with PVT Lab Test Tuning module. When you press it, a new window will be open. As explained before, this window has many sections: the composition info, the settings, experimental data, and the saving experimental data on a database, and then there's grids and there's the buttons. Okay, so the first thing I need to do is to just let know HydraFLASH which fluid I want to tune the model parameters with. Okay, so in this case, I want to choose reservoir fluid, table 3.7 of Pedersen book. I want to tune this fluid. And the second thing, I need to tell HydraFLASH which experimental data I have. You can see 6 checkboxes here. If you check any of them, the relevant tab here will be opened. If you uncheck it, it will be disabled. And then if you check multiple of them, multiple tab will be open, and you can enter as many as data as you can. But for now, let me uncheck this. I have the results of constant mass expansion, or CME experiment, at 97.5 centigrade for the old mixture in the composition shown in table 3.7. This is the exact fluid that we have created here. So this is the CME data for this fluid. Okay, so I want to tune this fluid with CME data. Okay, so what I need to do is to enter, let me move these windows a bit. I need to enter this data into HydraFLASH field. Okay. Okay, so I tell HydraFLASH, you see that these tabs are disabled, so I need to tell that which data I'm going to enter. This is CME data, and then change the units that I have. It's centigrade, it's bar. Okay, that's very good. If it's any the units are different, for example, you are in Fahrenheit, you just need to check the Fahrenheit, it will change. Can change the units here as well, but my units are in bar, so that's fine. And then enter these data one by one. When you want to add a new stage, new set of data, you need to press this button, this green plus button. Just press it, and then the empty field will be appear. You can change the units, and you can enter the data here. And in this button, it takes the gas composition for this stage. So if I press this button, a new window will be open, and I can enter the gas composition corresponding to this stage. Okay. Okay. So for this data, I have let me change it to a place that I can have both files open. Okay. So I have entered this one. The pressure is 351. The relative volume is the VSAT is 0.9765, and the compressibility is move it a little bit, is 0.00185. If you don't have access to any data, just leave the field and the place blank. And the Y factor, This is higher than the saturation properties, so I leave it as it is. And then I need to enter the saturation temperature for this experimental data. The saturation temperature, as explained here, A, is at 200 bar at 97.5 centigrade. Okay, so that's fine. And then you enter all these data or a fraction of it, as long as you want. If you want all of it, you just enter all of it. But it takes a little bit time, so I'm going to enter everything here. Then I will be back. Okay, now I have entered all the data from start to beginning. Saturation, the saturation data is here, and let me double check with the Excel file I have, and okay, that's fine. It's the same data here. Okay, and the units are fine. Now I take a few minutes to enter all these data, so I don't want to spend all this time again to enter the data if I want to tune the model again. So what I can do is to either start tuning, but it is recommended, we highly recommend that you save these experimental data to database. When you save these experimental data, it reads, okay, which fluid is active. Then it attaches this experimental data to the active fluid. You need to be careful that many fluids, one fluid can be connected to many experimental data, but one experimental data can only be connected to one fluid. If you want to connect the same experimental data to a different fluid, you need to enter them again. But in terms of how it is saved on the database, one experimental data can only be connected to one fluid, but one fluid can be connected to many experimental data. Okay. Now I call this experimental data to table 3.6. I call this CME underline table 3.6 so that I can remember. And when I choose a dataset name, I just press save experimental data. That's it. It has been saved. And now it is active. Now I can start tuning. But before starting the tuning, you can change the settings. Okay, in these settings, you can see 3 sections. The first section is the EOS variable. By checking these values, you are telling HydraFLASH which model parameters you want to change, you want to tune, you want to adjust. If you uncheck it, the HydraFLASH won't change this parameter. We recommend that leave all these parameters checked because it helps the tuning. And but if you don't want to change anything, just uncheck this. In this section, the variable components, it means that these parameters, which for which components you want to tune the parameters for. So if you don't want to change, if you only want to change the parameters of the plus fraction, you just need to uncheck all these components and just leave it checked. And then it only changes the parameters of this compound. But again, we recommend that you leave all of them checked. It helps the tuning procedure. And because these parameters for known components like methane, ethane, propane, carbon dioxide or nitrogen, cannot change them. It's deactivated. Okay. As I explained before, you can change the weighting factors as well. So if you go to the CME, you will see all these CME experimental variables, and it is already saying, you can see that there are many values has been assigned to different parameters. You can see the values for some parameters are higher than the others. What does it mean? It means that by default, I have told HydraFLASH that the saturation properties, the density of the liquid and gas, and the volume fraction is more important, for example, to the gas composition for me. If you want to change it, you can just slide this slider, this handle, and for example, if the saturation pressure is of less importance for you, you can either enter a number, or you can slide this slider to a high value, 100% or any value. This value is just an indication of importance between 1 to 0. So if you want to tell HydraFLASH how much these values are more important for you to be tuned, you just assign a value between 0 and 100. And when you enter these values, you just press save, because I didn't change anything, so I just close this window. I have saved my experimental data, and it is connected to this fluid. Now I can start tuning. So to start the tuning, I just need to press tune model. And you can see that it is shown here how much is the objective function in terms of the absolute average deviation percent in the back end. So it means that you are seeing how the tuning procedure is going. So now the AAD, the average AAD, the deviation from all these experimental data is now 0.35. That it means that the tuning is going very well. So I just need, and after a while it remains constant, which means that it's getting converged. So I just need to wait until it is done. Now it is done. It tells you how much it took time, 40 seconds, number of iteration 100. The objective function in terms of the AAD is now 0.34, and the correction factors to some parameters are shown here as well. So you just check if you're happy with the tuning report, which the most important part is this value. If it's small enough, then it means that the tuning has been successful. If you're happy with it, you just need to add it to the database. But before adding it to the database, you can change the name. And I recommend that you change the name, a proper name, so that you can, by seeing the name, you can recognize, okay, this was the fluid that I tuned with the CME data. So I put CME tuned, and then I can press add to database. Now it says that it has been added to the database. Now if you go to the fluid management tab, you see that the tuned fluid is now activated. You can start performing calculations with this fluid. Okay, let's go back to the tuning window again. You have two other buttons here. Let me load. Okay, let me change this first. Okay, so let me load this experimental data and show you how loading works. So you go here, the activate fluid is this, and just activate this and press load experimental data. See, all this data that I have entered is now loaded. Okay, but let's try something else. Go to this one. I activate some fluid else, natural gas, and I want to load the CME for a natural gas, and I press load data. It gives you an error. Say the selected experimental data has been saved for another composition. Please load the relevant composition and try again. And it also gives you a hint of which of the fluid that this experimental data has been tuned for, has been entered for, saved for. And it gives you the date and the name of the composition so that you can find it easily. If by any chance you have lost that composition or you have deleted that composition, you need to enter the experimental, you need to create the composition again, and you need to enter experimental data and save it again. Okay. So let me go back to this one and load experimental data. Okay, that's fine. You have two buttons here. This clear data, clear everything. Let me press it. Now it's clear. And if I want to add again, I can check any data I have, the viscosity, CME, anything, and you can enter data here. Let me clear it again. And let me load this experimental data. Okay, now it is loaded. Or if you want to have all these experimental data in an Excel file, just press export to Excel. And then an Excel file will be opened. You have the fluid information here. Okay. So, and it tells you what if this fluid, what is it? Is the project is HydraFLASH course, the owner is HydraFAC, it's oil, it's a live sample. It has been created for some hydro calculation. It's uncontaminated, characterized, no, it's not characterized. And it also shows you whether this fluid has been tuned before or not. And you have different type of experimental data, and it shows that it has not been tuned. And also you can see the composition of the fluid. Great. Now let me close this experimental data in the Excel file. Okay, so when a fluid is tuned and it has been connected to an experimental data, you can repeat everything and see actually how the tuning went. So for that, you can use this simulation button here. It will open another window. This simulation repeats all these calculations for CME and compare the predictions with the experimental data. But for this experimental data, you need to load two things. First, the tuned fluid. So I named this tuned fluid CME. It shows you here, see that LED becomes green, and shows that it has been tuned with constant mass expansion, CME data. And also it shows you which experimental data are connected, which experimental data, this fluid has been tuned with which experimental data. And this connected experimental data, the name is there, CME table 3.6. Why it gives you that? Because you need to load the experimental data as well. So you read this name, okay, if you imagine that you have many experimental data, it gives you a hint, you just need to select this. And when a tuned fluid is active and the relevant experimental data is active, you get a green light here. If you don't have, let me change it to mud. See, first of all, you won't see anything that is connected to this fluid. All the LEDs are red. That means that this fluid has not been tuned with anything. And the match experimental data LED is also red, which means this fluid and this experimental data are not matched. They have not been tuned with. So, okay, so you get through green lights first. this fluid has been tuned with mass expansion. It tells you which experimental data has been tuned with. If in this set you have many experimental data, all the data that you have in this set will be green. And then because this fluid has been tuned with exactly this data, you get a green light here. Okay. So when everything is ready, you can proceed and run simulation. Okay. So I press run simulation and this tab will be open. If you have many experimental data sets in one experimental data, different expanders will be opened. So to save the space, because it takes a long space to show all the data, we have put them in different expanders. See, if you want to open them, just click on them, and then if you want to close them, just again click on them. So the CME data, I have it here, and it tells you first the experimental pressure, the densities, and it gives you 3 values for each parameters. The tuned values, so the predictions after tuning, the predictions before tuning, and the experimental data. For example, for gas density, you can see that the tuned model is different from the predictions after tuning is different from before tuning. But I haven't entered any experimental data for gas density, so it hasn't tuned it. But for volume factor, if you see that this value, the predicted formation factor is closer to the experimental data than this value, than the untuned model. So that means that tuning was successful. If you see any dash here, it means that either you haven't provided in the experimental data, you haven't provided anything. Or when you provided the data and then you see for untuned the dash, it means that without tuning, the model cannot converge. So the tuning can converge. So for example, in this case, the model before tuning couldn't converge at this pressure, just below the saturation properties. But after tuning, it converged and is close to the experimental data. Okay. So the other thing is that if you want to change the units just before performing any simulation, you can tell HydraFLASH which units are your desired units. So let me close this one and then open simulation again. Said okay. Now I have this data. I know that this has been tuned with CME, and this is the relevant experimental data. And but I want to give the data in Fahrenheit and PSI. So PSIG, for example, gas density is fine, and the compressibility 1 PSI. Okay, so I define all the units and then press run simulation. It gives you all the predictions in the desired units. You can also copy these values. Just press Control Enter. Control C, and it will copy all these values, and you can copy it into an Excel file. Okay. Okay, close this. You can also, if you have different sets of experimental data, but as long as these different experimental data are connected to the same fluid, for example, I have CME table 3.6 and I have DLE table 3. I don't know, 10, because we don't have the many data for this fluid. So I have two experimental data for the same fluid. And I have saved these two data not in a one experimental set, in two experimental sets, one CME and one DLE. You can load the first one and the second one as well. So let me show you what I mean. So let me close this one and open it a new one. So for this fluid, I have saturation properties as well. So I say saturation properties. I add, it is a bubble point. Okay, so it's 97.5. The pressure is, how much was the pressure? 200. Let me see if I have the saturation liquid density. Don't have it. So I just put a number, 87, or maybe 6. Just a random number, which makes sense. And then I press saturation, and then I press save experimental data. Now, with one fluid, the reservoir fluid T 3.7, I have two experimental data connected to one fluid. I can do that. The opposite is not possible. I cannot connect one experimental data to different fluids, but I can connect one fluid to different experimental data. So what I want to do is, let me close this one again. I come back 2 days later and I want to do tuning, and I say, okay, I have saved the saturation for this fluid, but at the same time, I want to include saturation and CME and DLE and any other saturation all together. I want to tune the fluid with every experimental data I have. So what I can do is load experimental data and then select this one, press load again. So now you have two sets of experimental data showing here. Now you can save these two as a new single file, which is all data. I call this all data, and press save. So if I come back, now I have 3 experimental sets. All data has saturation and CME. CME only has CME, and saturation only has saturation. So by this, I mean that you can merge different experimental data. So one point, it's if you have for one fluid, if you have CME, saturation, and viscosity data, it is better to enter them in separate data sets, and then if you want to combine them, it will be easier for you. But if you enter them in one single, everything in one single, then you cannot really change it. But if you enter viscosity in one experimental set, CME in one experimental set, and for example, DLE in one experimental set, then you can combine them however you want. Or you can tune it with one single, one of them. Okay. I think I have covered everything for CPA model tuning and PVT Lab test model tuning. And any other experimental data set is the same thing. You just need to enter data, you just need to change the units. If you have a gas composition, enter the gas compositions here. And then as long as you remember which, you just remember to save the experimental data you save. But if you don't save it, you probably you will lose the experimental data if you close HydraFLASH or if you close this window. So remember that save the experimental data so that you can have the experimental data saved on the data.